This is the inner solar system. Can you guys see it? Kevin T, give me one of these if you can, please. Thank you, Kevin. Yeah, I appreciate it. All right, so this is the plane of the Earth's orbit. So if I tilt it, you guys can see the plane is like a sheet of paper, like that, right? And like nothing to it. Seems like all the inner planets, anyways, they have the same plane of orbit, pretty close, within just a few degrees of each other. That's why we think that maybe the entire solar system was made from one single rotating cloud of gas, that eventually this gas came together and made all the planets. You know, the gas became particles, particles stuck together, eventually getting bigger. Snowball effect made it bigger and bigger and bigger. Eventually all the planets formed. But I want to show you something. Mercury is the one with the reddish orbit here. Then white orbit is Venus. Then green one is Earth. And the orange one is Mars. So let's see how they move. Look at that. So check it out. See how much faster Mercury goes than Mars. See how much faster Earth goes than Mars. See, we're going to catch up with Mars here. We're going to catch up, catch up, catch up. We just caught up with Mars. Now Mars appears to go backwards. Retrograde motion of Mars. Now when we look at Venus and Mercury, the retrograde motion is also happening, except it kind of in reverse, right? Because they're passing us instead of we passing them. So it's the same old story. In the freeway, it's the same thing. If you pass a car, it appears that the car is going backwards. If a car passes you, then to them you appear to go backwards, right? And so either way, they appear to move in the sky. One way, after the retrograde motion starts, they go the other way. So this is a backwards motion from the apparent motion they already have, right? All right. Now keep this in mind. I was going to show you guys the outer solar system too. This is the outer solar system, and this outer solar system.
The astral plane.
I'm sorry?
What did you call this? What plane?
Earth's orbital plane.
Oh, orbit. Thank you.
Orbital plane. The plane
of orbit. On the same degree.
Yeah, the Earth goes around the sun, right? Mm-hmm. And it's always in this sheet of paper we call the orbital plane of the Earth. Okay. In fact, do you see this sheet here? Mm-hmm. This green sheet that represents the Earth's orbit. Mm-hmm. So the Earth is always in this orbit, always. So we call that the plane, P-L-A-N-E, not P-L-A-I-N, like plain yogurt. This is a plane of the Earth's orbit, right? So there's a plane of the Earth's orbit, and the Earth is always on it. The rest of the planets are pretty close. Look at that, pretty darn close. Except this one out here, that's Pluto, which they kicked out. So Pluto's orbit is way off. If you look at it.
The reason it was kicked off being a planet status?
Right. See, look at that. It's 26 degrees off. So there's an angle between it and the rest of the planets in the solar system. You see it?
Mm-hmm. Is that why they made it? Is that why they said Pluto is not a planet? Because it's not on the same orbital plane?
No. They kicked Pluto out because very close to orbit of Pluto, they found a whole bunch of other objects, and a couple of them turned out to be bigger than Pluto itself. Oh. So if they were going to call Pluto a planet, they have to call all the other ones planet too. So they decide to have a new, system to call them. It's a really goofy system, by the way, and they call them all dwarf planets. But what's the difference between, let's say, there's a dwarf and a person that is a dwarf? It's still a human being, right? Mm-hmm. So a dwarf planet is still a planet, isn't it? It's kind of ridiculous, right? So yeah, but I guess I'll tell you now. What happened is that the astronomers all left the meeting in Prague. Prague makes the best beer in the world, even better than Germany. So they had a meeting for 3 days and they all attended. The last day, there were only dynamics, people that talk about like orbits and stuff, left. Like if, I don't know, less than 100. And then they went and got drunk and lunch. They came back after lunch. They kicked Pluto out of the planetary world. But before they kicked Pluto out, they had some, reason 1, reason 2, reason 3, why Pluto is not a planet, and why the other ones are a planet. And those reasons were totally insufficient, and it was made by drunk people. So then they went back and they revised it, and they keep revising it, but I've never seen a good explanation of what a planet is, what a dwarf planet is. It doesn't make any sense to me anyways. But who am I? These guys are all PhDs from Caltech. So, whatever. All right, so let's get flying here. Now, what we're going to do today, we're going to look at this whole solar system from a vantage point of the 16th century, right? So in the 16th century, that was like the beginning of telescopes, and the biggest contribution to the planetary systems, solar system, was made by two people, Tycho Brahe or Tycho Brahe and Johannes Kepler. These two guys, without a telescope, they didn't have any telescope during their entire life, but they made huge, huge leaps in understanding the solar system's motions and how planets are, spaced out and everything else. All right, so let's take a look at these guys real quick, then I'll get on the board and show you guys all the laws that we have to follow to understand the laws of the planetary motion by Mr. Kepler. Now, this is Tycho Brahe. Tycho Brahe is Danish. It means he's from Denmark. And he is considered to be the party animal of the astronomy world. So he partied more than any other astronomer, probably. I don't know anybody that has partied as much as Tycho Brahe. Tycho Brahe was born a rich man. His cousin was the king of Denmark at the time. Born in 1546, that's the middle of the 16th century, and he dies at the very beginning of the 17th century. As you notice, he didn't live to be very long, right? What is it, 55 years, I think? 55 years, and there's a reason for it. He loved the two things even more than astronomy, I think. One was drinking beer. He loved drinking beer. And we're not talking about drinking like a couple of bottles of beer. We're talking about gallons of beer. And also he loved prostitutes. Those two things were pretty awesome to him. When he was 18 years old, he goes to a bar. He goes in a fight with some other guy over a prostitute. They get in a sword fight, and the guy cuts off his nose. That's why his nose looks kind of half done, right? This is a gold nose. He was rich enough to make a gold nose, and this gold nose is in the museum now. There is his gold nose, you guys. So this is history. And a lot of his pictures actually look like this. You can't even tell where, the gold nose starts and his real nose starts. But, we can't make fun of people's, disfigurement. But we can make fun of his excessive drinking. I mean, the guy drinks so much that incredible things happen when he drinks that much. So he talks to his cousin, the king of Denmark, and he says, "Can you buy me an island, please? I want to do some astronomy." That's what I told my dad, but, didn't work. But he bought him an island. So he was given an island. This is the island of Vin. H-V-E-E-N. Vin. Which basically is heaven, right? Heaven. So on this island of Vin, he builds observatories. Without a telescope, he builds observatories to measure the altitude and the azimuth of the objects. Now, if you watch the videos that are put there for you, you'll see what altitude is, how many degrees above the horizon an celestial object is in the sky. Azimuth is how many degrees east of north something is. So just two numbers for his observations. He would look at a star, go, okay, this is, altitude this, azimuth this, altitude this, azimuth this. And he put down dates and times of observation in a book. Now, what did this place look like? It looked like this. Pretty amazing. Like, it's a beautiful place. And you can go there today. And it was destroyed during the Second World War, this island of Vin. And the Allies destroyed it. The British, the Americans, they bombed the island. They destroyed all the observatories. And of course, after the war, we rebuilt the observatories, right? And there you go, tax dollars at work. So we rebuilt it even better than new. So now if you go there, you can go around the entire island on free bicycles. There's a whole bunch of bicycles just sitting there. You don't have to pay anything. You just ride the bicycles around the island. It gets pretty cold though. It's between Denmark and Sweden. Nowadays, it actually belongs to Sweden. They must have a war. I didn't read the history of what happens to the island afterwards. So it kind of looked like this. They had little observatories in all the corners of the island here. And this is where they measured all the angles. Now, he's famous for building the instruments, Mr. Tycho Brahe, very famous instrument builder. He's also got eagle eyes. He could see things that no other human being has ever seen. So he has super eyes. Without a telescope, he made these fantastic measurements, incredible measurements of Mars specifically. He loved Mars because remember, Mars gave the geocentric people, people that believe the Earth is the center of the universe, the biggest problem. It was the retrograde motion of Mars that gave them all the trouble. And so this is Mr. Tycho Brahe inside his observatory with one of his assistants here. He is supposedly he would observe something and then he'd tell his assistants what he's doing. This is a very famous picture, by the way, and this is his famous dog at the observatory. I think his name was Tito. All right, and then this is one of his instruments, and you can move this around any direction you want. This ball is attached to this measuring instrument. It looks like something that you would use in the middle of the ocean to get the altitude and azimuth of the sun, right? So it looks one of those fancy instruments, all beautiful and everything. And you move it by moving the sphere inside of this globe here. So that's a very easy way to move things, very, very nicely done. Okay, let's see. Now, he had this huge book full of observations of Mars. He was very excited, except he didn't understand what he was writing. He didn't understand, well, what does it mean? I have all these observations. He needs a mathematician. So he found a mathematician in Germany. This guy was different, a little different than everybody else. His name is Johannes Kepler, like John Kepler, Johannes. So John Kepler was a teacher, math teacher, and he was a terrible math teacher, better mathematician. He was a brilliant mathematician, actually. And by studying all the information from the book of Tycho Brahe, he was able to figure out the entire motion of this planets in the solar system. Now, what he figured out doesn't just work inside the solar system. He can also figure out motions of black holes and other stars, stars orbiting other stars, galaxies orbiting other galaxies. He can figure out any orbits, not just in the solar system. Brilliant guy. He did have, some quirks. One of them was that he thought that God is perfect, so that every shape, like the orbit of the planets, have to be circular. And the Earth had to be a sphere. The planet had to be a perfect sphere. So he wasn't really into the perfection of God, because God doesn't make anything imperfect in heaven anyways. On Earth, everything was imperfect, but that's the devil's work. So he could also hear the music of the spheres as well. And if you ever hear the music of the spheres, that's Kepler's thing, right? The music of the spheres. He also is going to write some books too. All right, so now I am going to get on the board now, and we are going to, now you guys were looking at the pictures, right? Were you guys looking at the pictures or not?
Yeah, we were.
Yeah, okay,
Yeah.
good. All right, all right, so I'm going to change cameras and get up there on the board. So we're going to be talking about Kepler's laws, what he actually figured out. And it was an incredible thing, right? Well, here's where this incredible thing starts. It starts when this guy, Tycho Brahe, goes to Prague. Prague is the capital of ex-Czechoslovakia, which turned into Czech Republic, then changed name to Czechia. Now they call it Czechia. So Czechia, Czech Republic, Czechoslovakia, that's where Prague is. That's the capital. But Prague back then, in the 16th century, was an actual country. It was a country of Prague. And they had a king of Prague. So he was really into drinking beer at the dinner table. He would bring prostitutes to the island. And Kepler was a man of God with his wife and kids sitting at the table. He was kind of upset. So they didn't get along very well, and he only gave him like one page every few days and go study this. He had thousands of pages of observations, but he would keep it from Kepler. I mean, why hire somebody to do the work when you don't want him to do the work? I don't quite understand. But he had his own reasons, I guess. He didn't like Kepler. Kepler to him was a straight guy, and to Kepler, he was just a party animal that really didn't deserve all the money and accolades. All right, so he goes to one day he goes to the king of Prague to drink some beer with him. So Tycho Brahe, king of Denmark, sit around, they drinking beer. But they don't just drink beer, they drink beer. And they drink so much, and as the story goes, his bladder burst at the dinner table. I don't know if that story is true or not. There's other stories. Other stories says that all his life was his drinking alcohol, and that destroyed his, his entire insides basically. So his kidneys were so bad that his kidneys failed at the table and he died. Another story says that he was on his carriage going home, and that's when he felt sick and he died. Regardless, he dies. And when he dies, everybody in the island, all the assistants, they grab all the expensive instruments, except the ones that are super heavy. They just leave them behind. And they leave. But Kepler stays with his wife. And the story says that he may have stayed there for like 10 years afterwards. Why would you want to leave heaven, right? So he stayed in heaven. Now, his wife and kid actually helped him quite a bit because he had to do some measurements that required calculus. But calculus was not invented yet. Sir Isaac Newton and this other French guy, either way, there's a discussion about who invented calculus. They're going to invent calculus in the 17th century. So for now, he's stuck. And he has to use manual labor by his wife and kid. So like as an example, how do you get the area of a shape like this? Look, a shape like this. How do you get the area here? There's no formulas for this, right? How do you get the area? It's not a triangle. It's not even a slice of pizza. It's not even symmetrical. How do you do that, right? It's an impossibility. So what he did, he sliced it down to little thin sections here. And then he measured the little squares like this. So like one area here, this area here. It took years to figure out the area of something like this. And he had to do it multiple times. So he had a tough time, but he did it. His wife helped quite a bit. So afterwards, he came up with these laws. After 10 years of working, he finally finished his third law. So he's got 3 laws. Number 1 law, very simple. He talks about the orbits of the planets not being circular. He's devastated. God is not perfect. Instead of circular orbits, he ends up with elliptical orbits. Now, what the heck is an ellipse? An ellipse is a shape like this. Here's an ellipse. Right, here's an ellipse. Looks kind of like that, right? So the ellipse is special. In fact, a circle is an ellipse. So an ellipse is not a circle, but a circle is an ellipse. So what's so special about this ellipse? Well, it's got 2 points in it called foci. Foci means 2 focuses. So foci is plural. 2 foci. Focuses mean foci. So foci means focuses. So this is 1 focus. Here's a second focus. What's so special about this focuses or foci? What's so special is that from the perimeter of the ellipse, so this is the perimeter. Perimeter, right? Perimeter of the ellipse. You can choose any of these points on the perimeter, any one. Like let's say we choose this point, and how about this point? All right, so we choose those 2 points. The distance between these points and the 2 foci is always the same for a given ellipse. So let's take a look. Like as an example, I'm going to draw a line between the focus here and this point and this point here. Let's call this like A, let's call this B. Now let's draw lines from this point now to the 2 foci. This one here and then this one here. Let's call this C, let's call this D. So you can say that A plus B is equal to C plus D. A plus B is equal to C plus D. Now you can use this to your advantage. If you want to draw an ellipse, it's very simple. What you need is a cork board. You put a couple of pins in a cork board like this, and you get a loop of a string. So you get a loop of string like this. You put it around here, and then you put your pencil inside the loop of strings. Then you pull it tight, and then you start moving it. As you move it, you automatically draw an ellipse. Why? Because the distance between any point in the perimeter and those two foci, they're the same, right? They're constant. So you could draw any ellipse given these 2 points. So you basically choose 2 points, put a loop of string around it, you stretch it tight, and then you just move. As you move, you automatically draw an ellipse, right? Okay. So that's what's so special about an ellipse. Before I go to the second law, I need to give you one heads up. You're going to need a calculator to do something here. So like on the exam, not this weekend, but the next weekend, you need a calculator, and the calculators are normally in your cell phone. So you'd be advised to use a cell phone now, like maybe even today, and practice to see if you can use the calculator. Because the calculator becomes a scientific calculator. Let me show you. Like here's my calculator. Like this. That's a calculator, right? You can add, multiply, subtract, and stuff. But if you turn it around, it becomes a scientific calculator. So it's got square root, cube root, and things like that. You're going to need that. So just be advised that you want to maybe practice with your cell phone and your calculator. All right. Okay, so let's get going here. I'm going to erase this and give you the very first law of Kepler's. The first law talks about the shape of the orbits. He says the shape of the orbits are elliptical. And he also gives us the position of the sun. So it's got two things: the shape of the orbit of the planets and the position of the sun, right? Those two things. So let's see. The first law says Kepler's first law, Kepler, number one law. It says planets. Now he's only done Mars, but based on Mars, he made his law, right? So he's assuming that all the planets are doing the same thing. Planets orbit the sun. In elliptical orbits with the sun in one focus. That's all. Very simple, but two things: the position of the sun and also the shape of the orbit. So he says they're elliptical. That's one. And he also says the sun is here. So here's the sun. The sun. What about the other foci? Well, there's nothing there. There's just space in the other foci, right? So there's nothing here. Nothing. Nothing, and then the sun. The sun doesn't move around, back and forth to the other foci. It just stays in one foci. So there's one thing that we'll talk about maybe on Thursday, actually, and that's this. The planets, or even the moon going around the Earth, it doesn't go around the Earth. It goes around the center of gravity of the Earth-Moon system. So the moon doesn't go around like this. The Earth also moves. So as it goes around, the Earth does this. The Earth goes around the center of gravity, so does the moon. That's something that we're going to discuss probably on Thursday, because that's Newton's law, right? Okay. Any questions about number one law then? So it tells you that a planet is orbiting in an elliptical orbit, and the sun is in the foci position of the sun. That's all. Law number 2 gets a little more sophisticated, and it's very difficult to digest for most of the students. So I'll try to make it kind of like with today's language, I'll try to kind of improve on the 16th century language. So let's see how that works. So this would be law number 2. So law number 2 says a line joining a planet and the sun sweep out equal areas in equal interval of time. What the heck does this all mean? Right, so we say a line joining a planet and the sun. Oh, what kind of a line are we talking about? Well, today's language, I would say, what should I call it? God, it's just like on the tip of my tongue. The thing that you grab and put it on the bridge and you jump off the bridge with?
Bungee jump.
The rope?
A bungee cord, right? That's what it is, a bungee cord. So we're using a bungee cord between the planet and the sun. So we tighten one end to a planet like the Earth or Mars. The other end, we tighten it to the sun. Imagination, right? So this line, he says, will sweep out equal areas in equal intervals of time. So what are we talking about, equal areas? Well, look, here is a board, right? As I move it, I'm sweeping out space, right? This is space. This is all space. And so as I move this thing, I'm sweeping up this space. I just swept up this much space was swept up by it. Now, normally you're used to sweeping with a broom on the ground. You just sweep it. But this is sweeping space, all right? So let's see how this thing is working here. That's why it's not so easy to digest. So I'm going to draw one more ellipse here. There's an ellipse again. And in this case, we're going to put the sun here. And there's the sun. And let's put a blue planet here, I guess. I'm going to put a blue planet here. And then I will have this blue planet connected to the sun with a bungee cord. Let's use a green bungee cord. So this is a big, long bungee cord. So this bungee cord gets smaller, it shrinks, it gets longer, depending on where the planet is. So as the planet moves, the bungee cord is moving, and we said equal interval of time. So we got to give it some kind of a period of time. Let's make it 30 days, a year, 2 years, whatever. Like, I'll make it 30 days. So in 30 days, let's say, the planet moves maybe this much. So it goes from here to here in 30 days. While it's moving, the bungee cord is attached. So the bungee cord is sweeping up the space, touching space, I guess. I know, it sounds silly. Okay, so it's touching space like that. So how much space is touched? Say this is area 1. This much area is touched, like that. Now we go, okay, so later on, the planet is closer to the sun. So let's say the planet is over here now. Now it's moving this way still, and in 30 days, same period of time, is over here now. So that bungee cord has gotten a lot shorter. It goes from here to here. So how much space did that bungee cord touch? Well, this much space was touched by the bungee cord now. Let's call this area 2. So what it's saying is area 1 is equal to area 2. That's what it's saying. That's it. That's the basics of it. So what does it mean? And why is he even saying this? Well, he doesn't know completely, doesn't know the answer yet. But he smells something. That's what he's smelling. What is he smelling? He smells this. Now, when the planet gets farther from the sun, it goes slower. When it gets closer to the sun, it goes faster. But just faster and slower is not enough. Proportionally faster and slower according to the distance. You see? So when you get to law number 3, then he actually expresses it with numbers. Here he's smelling something. There is something is proportional. Like there's something proportional about period of a planet. That's how long it takes the planet to go around the sun, period. And the distance between the planet and the sun. There is something there. It says there's proportional. He doesn't exactly know what that is. He'll tell us in the third law.
So, can I say something? So when it's further away and it's going slower, it has less space to cover in that little area, but it goes the same amount of time since the other part is going faster, but it has more space to cover.
Not exactly.
No?
No, what he's saying is there is a relationship, right?
Mhm.
Like a relationship would be something like this. You say there's a relationship between the area of a circle and the radius of a circle, right?
Mhm.
But if you don't know, you say pi r squared, right? You don't know pi r squared, but you know there's a relationship between the radius and the area, right?
Mhm.
But you don't know that it's pi r squared. You just know there's something there, right? So the pi and the r squared is something that you have to figure out. So he knows there's a relationship between the period and the distance. He doesn't know exactly what that relationship is. Do you follow?
Gotcha.
Once they give you the third law, then you see it. So like this. So he goes very slowly here. And then as he approaches the sun, he goes, wow. Like that, all right? Something like that. So we say when the sun is closer to the earth or the earth is closer to the sun, the planet goes faster. When the earth is farthest from the sun, the earth goes slowest. So as a planet approaches the sun, it goes faster. As it gets away from the sun, it goes slower. Proportionally though. What is that proportion? Let's see. So basically here, all you want to know from this is when a planet is closer to the sun, the planet goes faster. When it's farther from the sun, the planet goes slower. If the moon is closer to the earth, it goes faster. If the moon is farther from the earth, it goes slower. That's basically what we're trying to get to. Because the third law is going to give us numbers now. This is his masterpiece. It's his masterpiece, and it's kind of incredible, actually. These guys had no telescopes, and yet they figured out these laws with no telescopes, just with their eyes. Pretty incredible. So third law requires just a little bit of prep work. Let's see what we can do to prep you guys up. One thing we need to figure out is something called the astronomical unit. The astronomical unit is the average distance between the Earth and the sun. Because the Earth also gets farther from the sun. It gets closer to the sun. All the planets get farther from the sun, closer to the sun. Remember, the sun is at the foci, is one of the foci. And so because it's at the foci, all the planets get farther and closer. And when they do, they go faster and slower. So let's take a look. Here we have an ellipse again. Let's put the sun here again. Every ellipse has two axes. One of them is not that important to us. This other one is important. This is called the major axis. It goes from, there's the second foci here. It goes from the edge and the parameter through the foci to the other edge. And this is called the major axis. So that's the major axis of the ellipse. Major axis. There's the major axis. The minor axis is over here. It goes from the center top to here. That'll be the minor axis, but we're not going to use it, so but that's what it is. Now, 1/2 of the major axis, in other words, from the center to the edge here, right? This distance here. That's called semi-major axis. That's 1/2 of the major axis. So this is semi-major axis. So semi-major axis and the major axis, all right? The Earth gets, or any planet gets closer and farther. When a planet is closest to the sun, we say it's at perihelion. Peri, Greek, closest. Helion, the sun. So this means closest to the sun. Peri, closest. Helion. That's the sun. Closest to the sun. And aphelion. Farthest. So aphelion, perihelion. Perihelion closest, aphelion farthest. Now, if I want to get the average distance between the planet at aphelion and perihelion, can I express it in another way? Is there another way you can express that average distance? Like, what's the average between 13 and 11? What do you do? So you have 13 and 11. 13 and 11. What's the average between the two? Well, you add them up and you divide by the total number. So you add 11 and 13, that gives you 24. Right? So 13 plus 11 is equal to 24. And then you divide it by the total number. So you say 24 divided by 2, and you get 12. So 12 is the average between 11 and 13. All right? So now, what is the average distance between perihelion and aphelion for a point? Somebody tell me, so I can give you guys a point here.
Is it the semi-major axis?
Very good. That's right. Is the semi-major axis. Who said that?
I did. Andrew Farmer.
Farmer?
Yeah.
Yeah, we already talked about this. So thank you very much, Andrew. I appreciate it. That's right. So if I add this distance, perihelion, right? This distance to this distance, add this to this, divided by 2. What do you get? The distance from the center to the edge. Semi-major axis. So semi-major axis of the Earth's orbit is the average distance between the Earth and the sun. It's also called astronomical unit. That's what it is. So we say the astronomical unit. Astronomical unit is the average distance between the Earth and the sun. That I'll also put down here. Semi-major axis, semi-major axis of the Earth, or Earth's orbit. Sheesh. All right, so the semi-major axis of the Earth's orbit is the same as the astronomical unit. It's the average distance between the Earth and the sun. Same thing, this is all the same thing. Astronomical unit, the average distance, the semi-major axis of the Earth's orbit, they're all the same thing. It's about 93 million miles. So when we use Kepler's laws, we use astronomical units for distances. We don't use miles or kilometers or anything. Astronomical units. using the solar system. Now, is it silly? Maybe it's a little silly, but that's the convention. That's how we do it, all right? So now, what does the Kepler's third law say? Well, let's see what it says. Basically, it says P squared is equal to A cubed. So what's P and what's A? P is the period of revolution of the planet. Period of revolution of the planet. All right, that's P. So in the case of the Earth, it's 1 year, 365 days and a quarter. That's how long it takes the Earth to go around the sun, period. All right. So the period of revolution of a planet, whatever a planet is, to the power of 2. And it has a unit of Earth years. So I'll put down the unit. So you use these units when you actually calculate. You say unit is equal to Earth years. Okay, Earth years. Now,
That's
the
P.
power of 2, so you multiply times itself. Yes.
P is a unit of Earth years.
Yeah, P is Earth years. So like if the P was 1, that'll be the Earth. The Earth takes 1 year to go around the sun. So it'd be
Okay.
1 to the power of 2, as an example. If it
Okay.
was, let's see, if it was Jupiter, that would be 8 years. 8 Earth years. So 8 Earth years to the power of 2 would be 64, like that, right? If it was Saturn, it would be like 30 years. So it'd be 30 times 30, like that. If it was, if it was Pluto, it'd be 246 years. That's how many years it takes Pluto to go around the sun one time. It's a period of
Okay.
revolution, all right? Okay, so we use Earth years. Now, for A, this is the average distance between the planet, right? So A is the average distance between a planet and the sun. Planet average distance will be semi-major axis of your, planet's orbit, right? Whatever that is. But we use astronomical units here. Let me erase this. I'm just going to be perihelion is the closest to the sun. I'm just going to take that. Say this is perihelion. Perihelion. And so the unit here is equal to astronomical unit AU. That's astronomical unit. All right, so that's AU. All right. So when you take the average distance between the planet, any planet, and the sun, and the unit has to be in astronomical units. And if you take the period of the planet, that has to be in Earth years. And you put in this formula, it says P squared, period to the power of 2 is equal to the distance to the power of 3. It works out where most of the time you don't know the distance. What you have is like the period. So you look at this guy, you go, all right, so I know Jupiter was over there 8 years ago. It's back into the same spot now, right? So you check out to see how long it takes Jupiter to orbit the sun. All right, so I know it's 8 years. I have no idea what the distance is. You can put it in here and you actually get distance. Amazingly, it doesn't just work for planets though. It works for anything. 2 galaxies, 2 stars, 3 stars, satellite that goes around the Earth. So you just watch the sky and see how long it takes a satellite to orbit the Earth. So you wait, satellite comes back to the same spot. You go, oh, that's the period, like an hour and a half. Now what you can do is to find the distance between the Earth and the satellite. So you can figure out how far off the satellite is by knowing how long it goes around the Earth. That's like magic, like black magic, right? Something like that, right? So that's pretty weird that it works, but it works perfectly.
Could you put in use Jupiter as an example and
Oh, yeah,
do
go on,
this? Because
go on.
I'm
No panicking, we'll do that for sure. I'll give
you.
you many examples. Okay, so now, I just want to make sure you guys understand this is magical, right? It's magical. So now,
What is AU again? What does that say? Ast unit?
AU is astronomical unit, right here. Astronomical unit, AU. The astronomical unit. Okay. Now, let's do it, right? Let's figure this out. Can I erase all this now?
Yeah.
Okay, yeah, okay. All right, so let's erase this, get some room for examples here. All right, let's use Jupiter. And now let me do some simple stuff. So we say p squared is equal to a cube, right? What does that mean? That means p times p is equal to a times a times a. Right? That's what it means. A times, so a number times itself 3 times is equal to a number times itself 2 times. All right. So if I have p, then a can be figured out easily, right? So let's get p. So Jupiter takes 8 years to orbit the sun. So we go p. I'm sorry?
56.
So p is equal to 8 years, right? All right. So we say a to the power of 3 is equal to 8 to the power of 2, right? So what's 8 to the power of 2?
64.
That's right. So we go, okay, so A3 is equal to 64. So we're asking ourselves, what number times itself 3 times equals 64? What is that number? 4 times 4, 16. 16 times 4, 64. So then A is equal to 4, but how did I get it? I said A is equal to cube root of 64. That's the one that you need to use your calculator for, right? So is there something in the calculator that you can use to figure this out? Yes, and that is this. There's a button that says a little y here, a little x here. So you can put your x and y in there, and then you press your button, and it gives you the cube root, the second root, the fourth root, whatever, of x. So in this case, it'd be the third root, right? Okay, so we have a square root, like what number times itself, right? What's the square root of 4? 2. 2 times 2 is equal to 4. That's the square root of 4 is 2. And what about 9? 3. 3 times 3 is equal to 9. That's the square root. What about 27? What's the cube root of 27? What number times itself 3 times gives you 27? 3. 3 times 3 is 9. 9 times 3 is 27. How about 8? What's the cube root of 8?
2?
2. Yeah. What's the cube root of 64?
4.
4. Very good. Like that. All right. So what's the cube root of 125?
5.
5, right? 5 times 5? 25. 25 times 5? 125. Like that. Anyways, use your calculator. Okay, so now, in this case, what number times itself 3 times equals 64? So A is equal to 4. What's the unit here, you guys?
Astronomical unit.
Excellent, thank you. Astronomical unit. Who said that?
Claire Worth.
What's your last name?
WERTH.
WERTH.
Mm-hmm.
Okay, thank you. WERTH is correct. Thank you. All right, let's do another example. How about if P was 1, what is A equal to?
1, 1,
1, that's right, 1, right? So you go 1 times 1 times 1 is equal to 1. 1 times 1 is also equal to 1. So that's the easiest one. What planet would that be? 1.
Earth.
Earth.
Earth. There you go. Earth. That's right. Very good. Thank you, guys. Thank you. Okay. Let's do another example. Okay, so let me give you one that is a little difficult, right? And it also gives us a clue as to what the problem is here. Because there's a little problem. Isaac Newton is going to come and he's going to try to fix the problem, all right? Remember, when Galileo dies, Sir Isaac Newton is born in the 17th century. So it's going to have to wait. This formula is going to get modified by Sir Isaac Newton. And he's going to add masses to it. Let's see what he's adding masses. So Saturn is 1 billion miles away from the sun almost, right? So it's about 10 astronomical units from the sun. Almost 1 billion, right? Like 1 astronomical unit is almost like 100 million miles. So 10 astronomical units is like 1 billion miles away. So we go Saturn's distance, Saturn's A is equal to 10 AU, right? So what is P equal to now? So P squared is equal to 10 times 10 times 10, that's 1,000, right? That's 1,000. Now, P squared is equal to 1,000, so P is equal to just square root of 1,000. So when we do a square root, that means a 2 is up here. So what number times itself gives you 1,000? That's the question. What number times itself gives you a question? So you go to your calculator now.
31.62.
There you go. So you put your 1,000 in there. You press the square root and you get 31.6. Who gave me the 31.6?
William Yates.
Yates? Thank you, Mr. Yates. I thought your name was Billy.
Yeah, I go by either one.
Okay, thanks, Billy. All right. Yeah, my wife's son is also William. All right. So what is the answer then? 31.6. But you said 31.6. And so, Billy, what is the unit for 31.6?
The Earth years.
Very good. So this is years. That's right. All right. Very good. All right. So there's another example. Linda, would you like more examples? Or is that enough?
So that one we would always say years, definitely not astronomical units.
You can say years, yeah. Oh, astronomical units you have to say. But instead of saying Earth years, you can just say years.
Okay, but astronomical unit would be incorrect on that.
Yeah, this is years. A is astronomical unit, right? Look.
Yeah.
A was astronomical unit. Unit here is Earth years. So one of them has AU, astronomical unit. One of them is Earth years. Right? That's like a miraculous thing. But here's the problem. Linda, you never answered me. I'm sorry. Was that enough? Was that good enough?
I think it's enough.
Okay, great. All right. So now,
Sir, could you do one more for me?
Sure. Let's see. While I'm here, though, I like to do Saturn's case here. So remember, he only did Mars, right? He generalized for everybody, but he only did Mars. Well, it's kind of fortunate and unfortunate, right? It's fortunate because you got a chance to figure it out, because the orbit of Mars is pretty elliptical. If you'd done it for some other planet that was a more circular orbit, he would have never figured it out. And Mars was tiny. It was a big planet like Saturn that we just did. That would have been a problem. So the mass of the planet and the mass of the sun come into play when the planet is massive, like Jupiter and Saturn are huge planets. But he couldn't figure that out. So it turns out that Sir Isaac Newton is going to come, and he's going to put in the planets in there too. So you have to add the planets and multiply times the period to actually get the correct number, because this is, in actuality, is about 29.5 years. So we're getting 31.6. So it's not exact, right? Also, it's not exact because I gave you guys 10 astronomical units. It's not quite 10 astronomical, it's a little more than 10 astronomical units. So we didn't get perfect answers. One reason is he didn't know masses come into play. Because the masses come into the play is an interesting case. Because now, if you have the period of a planet and the distance, you can get the masses. So that's how we get the masses of the planets too. So you can get the mass of Jupiter by knowing how long Jupiter takes to go around the sun and what the distance is. Because we know the mass of the sun, you can get the mass of anything else. So it turns out, without this formula, we couldn't do anything. You couldn't go to the moon. We couldn't do anything, basically. So this formula is super magical. It's not just magical, right? Perfect. Okay, so let's do something else. Which one do you want? Do you want to do P or do you want to do A? So we can have anything. Let's see A and let's do P, because P is a little easier to get. You just watch the sky and you get the period. Not so difficult. Like around Jupiter, there's moons of Jupiter going around. You can figure out how long it takes the moons of Jupiter to go around Jupiter. From that, you can figure out the distance between the moon and Jupiter. From that, you can get the mass of the moon of Jupiter and so on. So let's do one. Let's say P period is equal to let's use 9. So that's 9 years. So a planet takes 9 years to orbit the sun. How far away is that planet? Even the question sounds magical. All I'm telling you is how long it takes the planet to go around the sun. You can figure out the distance? Wow. Right? That's pretty weird. So if a planet takes 9 years to go around the sun, how far away is that planet from the sun? Sheesh, right? So you go, all right, so A cubed is equal to 81, right?
4.33.
4.33, so A would be 4.33, and what's the unit?
Astronomical unit.
Very good, thank you. Yay. All right, who figured that one out? Was that you, Linda?
Yes.
Oh, I'm so proud of you. Linda's last name is Ulrich.
Mhm.
Thank you, thank you, thank you.